called okay. Good morning. Yeah, so this is tutorial number 10. Can we start now? Yes. Okay, last time we talked about partition. Yeah. When we use the partition algo, we just use the first element as the reference point, as the period. But you have something in your mind that if this one is not chosen correctly, then we'll make the algo not very efficient. Yeah? Because the algos should work like that. Half of them should be bigger than that on the other side. The other half has to be on the right-hand side. So if you do it in this way, the number of partitions you need to do will be smaller. The number will be smaller. You can try it. Yeah, if you have 7 elements, if you do it, if you always choose the biggest one as your period, yeah, then you have to do probably 6 or 6 times, say like that, or 5 times. Yeah, but if you distribute the element evenly on both sides, then probably 3 times, 4 times you'll finish it. Yeah, so you will have a gut feeling that we need to choose a correct one. How do we choose it correctly? That will be a mathematical problem, but okay, here we are using called the median. Yeah, so from statistics, yeah, you know that median is you have a sequence of numbers. The median is the guy in the middle. Half of the number will be smaller than that. Half of them will be bigger than that. But of course, if you have even number, 8 of them, one group should be 4, the other group should be 3. But roughly speaking, should be in this way, right? The median. Okay, so if we have an extra function to find the median from this group of elements. So we identify that, we use it as the period, as the reference point. We force it to be the leader of that. And then we'll use it to do the comparisons. So you will expect that half of the elements to be smaller than that, half of the elements to be bigger than that. So you keep doing that, the algo will be more efficient. So this is the advantage of these extra steps. Right? So it's okay. Why we need to do it? So we have to be careful. So not just do it, right? We have to know why we need to do it. So in this problem here, we will apply, it's similar to the previous one, but we apply this median function at the very beginning to identify it and put it as the first element for comparison. So it's okay? Yeah. Once it's okay, then we can see the corresponding algo here. So this median is not very, very time consuming. It's proportional to n. So it's roughly the same as the partition, right? So will not give it a very big burden for the partition algo. So like this. Okay, so we will not change the complexity of the algo partition. It's still proportional to n. Last time we proved that it's proportional to n, right? Now we have extra step, which is also proportional to n. So you add them together, it's also proportional to n. So we will expect that this extra step will not give a very big number of operation for the algo. So with all this, then we can go to the algo here. The algo here is like that. We have, last time we have the partition, right? Now we have partitioned, median partition. We use the extra one. First of all, we have to know how many elements there. So by this function, a dot last is supposed to be the number of elements in this sequence, in this array here, active elements. Yeah, the array you define maybe 1,000, but when you use it to hold the number is 100. So n dot last is 100. Okay, so now we call this function median. So what's that? We don't know, but we are given this one. We just use it, just like you use the calculator. Do you know that, or how do you get the number sine 45 degrees? Yeah, do you know that? You don't know that. How do they do it, right? 46 degrees, how do you do it? Yeah, you don't know. But you use it, you are very happy, you get the number, right? We are also very happy because we are given this function. Okay, so we use this function, and the return of this function will give you the position of the median. At which position is the median? Once we know that, the rank of that, the location of that, we swap it or swap it to number one. So that means we use it as the reference point. Okay. Then we continue to do the partition. Yeah, because once we have done that, the partition will use the leader, which is the median, as the reference point to do the comparison. We will expect that this kind of comparison will be efficient in that sense. Yeah, half of the number will be on one side, the other on the right-hand side as well. So is it okay? The algo is quite straightforward, right? Basically, we know the partition. Now we just add a few steps to it, get the median, and put the median as the period before doing the partition. Okay, so I also put a remark there. Now, if you use the median, roughly speaking, half the elements will be smaller than that, half of them will be bigger than that, right? So the extra step, you do the median, which is proportional to n, will make the algo here, the quickshot, more efficient. Yeah, later on you will see that, or the partition more efficient. Because later on we'll do the sorting. Actually, it's quicksort. Yeah. Okay, now. Any questions here? Any questions? How about the online student? Do you have any comment on that? Why do we need to do some extra work? Yeah. It's kind of insurance, right? You buy this insurance to make sure that subsequent partition will be more efficient. Okay. So can we move on to the next one? Okay or not? Okay, yeah. Okay, so when we use the question number one, write an algo that select the ith smallest element of A. In worst case, the complexity is still proportional to n. Prove that your algo indeed is proportional to n. Justify every steps, right? Clearly. So you see that in the selection sort, right? Selection sort, we are using it to do the sorting. Yeah, the algo is n squared. Is n squared. But this one is faster. is only n, or bubble sort, you see that is proportional to n. So it's quite efficient here. Okay, so this called select. Select is to select which one is what you want. But the select is you will choose the second largest, or the second smallest, or the fourth smallest. Maybe you have 100 elements in your sequence, 100. You want to find the rank, say 45. What's that? Or you want to find if you sort it and you just interested in the number, say one of the number, 54, say like that. The rank is 54 in this 100 number. So actually you are not very keen to know who is number 1, who is number 2, who is number 3. We just want to get what we want, right? Number 54. So this is different from the sorting. The sorting is we sort it from small to big, right? So we know each one of them. This is rank number 1, rank number 2, rank number 3, rank number 4, and so on. But now we may not need that. Yeah, we just want to know who is within this 100 element, who is number 54, say like that. Right? So we don't need to sort the whole array. To sort the whole array is more time consuming. We will try to get only the one we want. They are slightly different, right? Just like in this particular group of students, yeah. So we will sort it according to your height, say like that. I want to know who is from small to big, who is number 10. So who is number 1? Not my interest. Number 2, not, but we want to get the number 10. But of course, if you sort it from small to big like that, and then identify number 10, right? You overdo it. So you expect that you overdo it. It may not be necessary. It must be a better way that you can identify the number 10 easier, faster. That is this question. And you see that when you do the sorting, you have n log n. But now is just proportional to n. Different, right? N log n and n are different, right? So you have to count every sense. Okay, so let's see. How do we do it? So this is called not select. This one is new select. New select. Okay. Then the array is called A. Array is called A. Its index, the starting index is P. The ending index is R. And the one we want to find is the rank, right? I here. So later on, I have an example. I have example. Say P is equal to 100. The starting one is 100. The ending one is 200. So altogether, there are 101 elements there, right? But the one I want is not number 1, number 2. It's number 54 in this 100. 54 is the rank, not the index. So later on we'll see it. Yeah. Okay, so the algo is like this. If P and R are the same, that means the starting point and the ending point are the same. That means you have only one element. No need to do anything, just return up, right? So this is serve as a base case because you make it smaller and smaller and smaller. So eventually you will come to this point. Okay. So now you use the median partition. Is the one you newly invented, yeah, on previous page, right? So you find it you do the partition, you find it. Okay, so because you are using the median as the reference, so the median will be returned. The median will be returned. Once it returns, you get H. H is the one in the middle. Just like you have 100 elements, right? From 100 to 200, altogether 101 elements inside it. So the one in the middle, the median, should be, in terms of rank, is 51. 51, right? 50 elements are smaller than that. 50 elements are bigger than that. Okay, so it will return H. H is not the index, it's the rank. Rank is different because the starting point is 100, the ending point is 200, right? So you want the number. So later on, I is 54, but here H is the median. Median you suppose in the middle is the rank with 51 there. Okay, so but this one will give you the index of that. Yeah. So how do we find the rank of that? Of this one, it should be H minus P plus 1. H is the this one is P is the starting point. You add 1 to it, then will give you the rank of this one. So H is the index, K is the rank. They are different, right? They are different. So the H may be, in the example, if P is equal to 100, the ending point, the index is 200. So in this case here, H is the one in the middle. It will give you, in terms of number, will be at 151, right? But the rank is 51. Okay, so if I and K are the same, if I and K, because this one is in the middle. In this case here, the K will be 51. You can see that in the middle, right? The rank will be 51. If I is equal to 51, you hit the jackpot. That means you find it. I ask you, what will be the one number 51? Yeah. So if you hit it, fine. Then you return. Then you solve the problem. If not, what will happen? Because you have partitioned it into 2 parts. Yeah, maybe I draw a simple diagram. Let's see, the pen. Let's see that. Okay. So you see that I have this one. The starting point is P. The ending point is R. So H is in the middle. Right? And in terms of here will be the rank. The rank is K. This one is K. Okay. So if I ask you, say, if I want number 54, should we go to the left-hand side or the right-hand side? So you see that the starting point, is 100, P is 100, and R is 200. The one we would like to find is 54, the rank 54. But you see that the K here, if you count it, is 51. So we should not go to the left-hand side, right? We just go to the right-hand side to continue our search for this number 54, right? Is it okay? So we go to either the left-hand side or the right-hand side. For the left-hand side, we will go to search a smaller scope from P to H minus 1. P to H minus 1, because H is 151, right? So if I is greater than or equal to K, then you will go to the right-hand side. And then you start from H plus 1, which on the right-hand side, up to the last index R here. Now, so the rank here will be different, right? Because we are talking about 54. So in this group here, 54 is number 3 here in this new scope here, because we are talking about here. Should be the first one will be 52, 53, and then 54. So it's number 3. So the rank in this particular group will be I minus K. I is 54, K is equal to 51. The difference between them is 3. So we are talking about number 3, smallest guy on the right-hand side. Okay, so as you can see that in this example here, P is 100, R is 200. So we would like to find the number 54, the rank 54 there. So first, you find the median. The median is 51. The rank will be 51 in the middle. Okay, the number of elements smaller than that is 50. The number of elements bigger than that is also 50. Okay, so because 54 is bigger than 51, right? This one is rank is 51. So we will continue our search here on the right-hand side. You have to go to the right-hand side. It's okay. So we make use of the question number 1, what we have done. We newly invent that one, right? The median partition here. And we can find it. Yeah. Any questions here? So I use a particular example here to tell you that you have to know that the starting point is not necessarily 1 or 0. The ending point is not the number of elements there. Say we have 200, the ending point, right? The starting point is 100. So the scope we are talking about, there are 101 elements there inside. If you count it 100, 101, 1 to 200, 101. So the median should be rank 51. But the one we want to search for may not be number 51. Say, for example, if this is 54, you should go to the right-hand side. If you want to find number 10, then you go to the left-hand side, right? So, okay or not? Online student, do you have any other comments on that? Okay, so go to look at this one here. Slightly more challenging, yeah, right? Okay, so now we have to verify that this one is proportional to n. Yeah, so you see that if we do everything, use merge sort, is n log n, right? We use the quick sort, do everything to sort it before I identify number 54, n log n. You use bubble sort to do it, rank it, n squared. All right. So now we just interested in number 54. So we claim that this one is proportional to n, smaller. All right. So let's verify that. So from here, you can see that if P is equal to R, you have only one element, they are the same. you do very little things. You don't need to do anything. Yeah. So it's arguable, say that how much work, how much time we need to do it. You may assume that that is 1 unit of time, or maybe you say that, oh yeah, this is nothing, 0. Also can, will not affect the end result, but because this one doesn't count compared to other more complicated work. Okay, so let Tn will be the number of operation for an array of size n here. For an array size of n, how much time we spend on that? That is T of n. Okay, so T, if you have only one element, we assume that is equal to 0. Equal to 0. You don't need to do anything. Yeah, how do you sort it? Yeah, no need to sort, right? One element. So we assume that is 0. If you feel that may not be fair, you can assume it to be 1 unit of time. Also can, and will not affect anything. So since this median partition always partitions the array into 2 groups, right? One is n over 2, the other one also n over 2. But you don't take care of both of them. You just jump to any one of them, right? You go to the left-hand side or you go to the right-hand side. So although at the very beginning you have n values, right? N, but later on, once you jump to the left-hand side, only half of that n over 2. Or you jump to the right-hand side, also n over 2. So that's why we see that at the very beginning, we have n element, right? But after the first step, we have identified that whether we should go to the left-hand side and right-hand side. We only we are dealing with half of that n over 2. Plus Cn. Cn is what Cn? Cn is you use the median. You find the median, right? You need to be, you count it. That one is proportional to n. So it's C times n. This part here is for the median. Because in our algo, we first to find the median, right? The median is assumed to be proportional to n. So this term is for the median. So we have n elements. We do the median function, find the median, which is proportional to n. And then we are dealing with half of the elements. So you have to understand this line here. Okay or not? Okay. So now we try to simplify it. You have only one good method. What's that? Bedrock substitutions, right? So you use bedrock substitution to do it. Okay. So the first 2 terms is for n over 2. So you say that you divide into 2. So it's n divided by 2 by 2. So it's 2 squared. Plus, you see that for n over 2, you do the partition is n over 2 times c. So that is the partition for n over 2 elements. Yeah. This Cn is from the previous step is here. So you have to know what it is. Don't just look at it. I mark your quiz. I know that you up to here you have very, very funny steps, you see. I cannot understand. Yeah. So this Cn is here. This one here will be the first 2 terms. You use bedrock substitution. Okay. So now you are not very sure. You do one more step. This guy will give you another 2 terms. So one term is n over 2 to the power 3. Then this one you collect them together. Cn is the common factor. Inside it, this one will give you 1. This one will give you 1 over 2. And this one, we come to here, will be 1 over 2 squared. So you can see that the pattern is like that. Okay, so if you do it k times or k times, then will be n divided by 2 to the power k. So you see that this is 3, then you have 3 terms. So the first term is 1, the second term is 1 over 2, the last term is 2 to the power k minus 1. So this is not 3, all right? Although you count it is 1, 2, 3. This is 1, 2, dot, up to k term. So the last term should be k minus 1, the index, right? The exponent. So you use the formula to find the sum of them, the geometric series, right? The progression, yeah. So you find the answer. The answer is equal to 2. I will not do the detail. Now you are an expert. You are supposed to know how to do it. So at the end is t of 1 plus this is 2 is 2cn. We beautifully solved the problem, right? So you see that this one, whether you assume it into 1 or you can assume it into 0, it doesn't matter. Because compared to this one is much bigger, right? So the first term, t of 1 is negligible. We don't count it. Once we don't count it, it's proportional to n here. So it's big O of n here. We identify number 54 is proportional to n. How many elements there? Different from the previous algo, if we sort it, we do it thoroughly, is n log n. Then we identify number 54, n log n. But this one is proportional to n. It's big O of n. So this one should be more efficient, right? If n is very large, huh? Okay or not? So you see that it has its usefulness, right? Okay or not? Online students, do you see that? This one is backward substitution. Backward substitution, you don't learn it from what. Watch this one here. You have to do it on the piece of paper. If you don't do it, at the end you have you don't get 1. You may get 2. This 3 term is number 3. You have k term. This is k, like that. So you just miss a step. Then the whole thing, the key steps, the key steps should be there. You miss it. Okay. Okay or not? So this is backward substitutions. Yeah, because when I mark the one here, mark the paper, maybe only half of you or less than half of you know what's backward substitution to find this kind of one. It's not so difficult, right? Yeah, so but you just read my answer, you just unconditionally accept it. Yeah. Unconditional. Unconditionally accept it. Yeah. So you have to make your hands dirty. Try it. Try it. Yeah. Otherwise, only my hands are dirty. You are not dirty, you see. You cannot learn it. Okay, so let's move on. How about that? Next, consider performing counting sort on the following array. So what we are doing here is to find some funny sorting algo. This algo is better than n of n because we look at it, the worst case, worst not probably a bad case counter example, bubble sort, right? N squared. Then we have better one is merge sort, and then we have quick sort, we have heap sort, right? All of them are n of n. Now you see that we can find something here, this one proportional to n, big O of n, better than merge sort. So how come we don't use this one so often? Because it has its limitation, you see. Only certain conditions you need to fulfill before using it. Yeah. So let's see. This one is you have an array of integers here. For simplicity, we have 1 to 7, something like that, right? 1 to 7. But because when we sort it, it may be quite different from that, right? Maybe how tall you are, maybe you say that, oh, I think it's 1.71, say like that. So this one cannot, right? Because it's not for real number. This one is for integers. But if you are your 1 to 8, say that you are 20 years old, 21 years old, 22 years old, then this one can. This one can. Okay. Then this one can. If you round it to integers, okay. Or even your height here is 170, 171, 172, like that. So this one still can. But it's a real number, cannot, right? Yes? No. Okay. So remember that why we learned this one? Because it's special, right? Proportional to n. It's not n, not n. It's not n squared. It's fast, right? Proportional to n supposed to be fast, but it must be integer. Okay, so for simplicity, you see the number here is from 1 to 7. So first of all, we have this number here. We count how many 1 inside, 2 of them. How many 2 inside? None of them, right? How many 3 of them? Look at it. 1, 2, 3. So 3 of them. So you use the counter, you can count it. So the counter is a little bit strange, right? You have to digest it. You have to digest it. Make sure you know how to do it. Later on, you can do this one. You see that AJ is 1, 2, 3, 4, 5, one of the number here. So if this is number 3, then this counter 3 will be updated. You a little bit. The first time you see it, it's a little bit surprised, right? Yeah, can be done so efficient, right? So you have to make sure that it's part of your mind. You can use it, okay or not? Okay, so it's basically once you see 5, then the counter 5 will be updated. You see number 7, the counter will be updated. So of course, at the very beginning is initialized to 0, right? So after you check from the first index to the last one, all the elements, you will come up with this count array, right? Final count is here. So this one, you know how to do it, right? So this one is proportional to n. Can we say that? Because once you see 1, you update the counter. Once you see the second one, you update the counter. Once you see the third one, you update the counter. It's proportional to n. Okay, the next step. The next step is to find the cumulative sum of that. So how many elements are smaller than or equal to 1? 2 of them. So how many elements are smaller than or equal to 2? 0, 2 and 0 is here. How many elements are smaller than 3 or equal to 3? Is this one plus 2 is 5. Okay, 3 plus 2 is 5. How many elements are smaller than or equal to 4? Is 0 plus 5 is here. How many elements are smaller than or equal to 5? is 3 plus 5 is equal to 8, and so on. Of course, you can find other way. Not that efficient to do it. Mine is very efficient. Yeah. Okay or not? Basically, it's a cumulative sum. It's going up, non-decreasing. It's okay. This one. So you see that at the end, you know that you have 11 elements. 11 elements. Totally 11 elements. So now, how do you get this cumulative array, cumulative sum, proportional to n, right? Proportional to n. Once you see one, you just add together. Once you see one, you just add to the period sum, yeah, and so on. So it's proportional to n, okay or not? So everything is proportional to n. So at the end, we conclude that it's proportional to n. Next, how can we make the sorted sequence? Yeah, the sort array here is on the next page. Okay or not? Okay, let me explain to you. This 5, 7, 5, 1, 1, all this is the original array of elements. So these 11 elements are here. Okay or not? Nothing new lah. This one, what's this? This one is the cumulative sum, the array of cumulative sum. So you see that altogether we have 13 elements. Yeah, how come you have? Yeah, 13 elements. So not 11, 13 elements. Sorry, 13 elements. I may look at it wrong, Okay, so you see that how many elements here? 13 of them. So altogether is 7 numbers here. 7 numbers here. Okay, so now we'll try to create a sorted array. So we start from the end. Number 3, right? The last element is number 3. Number 3, where should we put? Where should we put number 3? You go to see number 3 is 5. Look at it, is 5. So you will place this 3 at array number 5. So you put 3 here. Okay or not? The correct position is for 3 is at the index 5. How do we get it? This is the value, you put it here. This is the index 5. Okay? Okay or not? The first step, okay. Now, so actually, this one is this one here. Now, once you do it, you see that you have used one of them here, apply here. So the accumulative here is no more than 4. So no more than 5. Now becomes 3. So the number 3, the steps here, you have to decrement this one by 1. Okay. This one is the last element. Number 3. You have settled. You have dealt with that. So now we go to the second largest, second smallest. Not second smallest. The second last element. Number 5. 5. Where do we put it? According to that, we go to 5, and you see 8 here, right? Under 5 is 8. So you put it at 8. You put it at 8, right? Once you put it at 8, you decrement this one to 7. Because you have find the correct position of that. So it's 7 now. Unknown is 7. Okay. So the next one we are dealing with is 6. 6, you see that 6 is here, right? 6 and then 6. We should put it at number 10. So number 10 is here. sorry, it should be here. 6, you look at it here because we finished this one. You look at 11. 11, we should put it at 11. Once we put it at 11, this one will be decrement to 10. So this one is 10. Okay, so we use this one to deal with the next 6. 6, this one is 10. So we put it at 10. And this one will be reduced to 9. Okay or not? Next, 1. 1, you look at it, is here, right? It's number 2. So we put it at number 2. Once you will put it at number 2, so this one will be 1. There's only one called 1 inside it because we have done this one here. This another one here. Okay, the next one is 3. 3, you see that is 4. So we put it at 4. We'll put it at 4 here. Previously, we have done it for this number 5 and number 4. Now, rank number, the index is 4, is 3. So once you have done that, so 3 will be from 4, you decrease it to 1. So the computer can do it very fast. The computer can do it very fast. But unfortunately, you have to use your supercomputer to do it. Okay, so you keep on doing that. Eventually, you will see that we'll put everything in. We'll fill up this one. And the rank should be, and this one should be sorted. So number 1, number 1, number 3, number 3, number 3, and so on until the end. You keep doing that. Now, so in this distribution here is also proportional to n. How many elements here, right? 3 steps only. Each one you have 3 steps. And then depending on how many elements you have. So this one is proportional to n. So at the end, it say that you have proportional to n plus proportional to n plus proportional to n, 3 steps, right? And the conclusion is proportional to n. Okay or not? This one, you have to do it yourself. This one is good for exam. Because the exam, I see the last line, I know that you are right or wrong, right? And then the exam, the reviewer look at it, wow, it has a lot of work, right? It has certain depth. Okay, but to our student, no problem. 99% can do it right, yeah, from our experience, yeah. This one is not a problem. They can do it very well, this one. Once you see it, you laugh at it. Wow, so simple, yeah. Not difficult. This one, some labor job, you see, yeah. Okay. We cannot set all the questions every time ask you to write the algo. You kill all of you on the spot, right? So must give you something good, right? At least doing all this, draw some table, draw some array, and then do some partition or sorting, whatever. At the end, you spend 2 pages, 3 pages on that. Wow. Very good, right? At least you will get 10 marks or 20 marks here. So must do it. Once you see this kind of question, yeah, you don't do this kind of question, you cannot survive. This one is to build up your basic marks. Just like your mathematical induction. Yeah. The first step is the basis step, right? To give you some marks, right? So the other more difficult, yeah. Okay, anyway, yeah. So any question on this one? So you look at my number 1, number 2, number. Okay, yeah. So So number 1. So I use number 1, number 2, number 3. 3 steps, right? For each number, you have 3 steps, so it's proportional to n. I don't go to the details, right? Yeah, but roughly you see that it's proportional to n. So you have 13 elements, so it should be 3 times 13, right? So how many steps you need to do it? Okay, so at the end, then you will put it back here. So it's proportional to n. So not everyone can be proportional to n. Only under very strict condition, then you can do it. N log n is very common, and it should be the norm. Proportional to n is very special case. Not everyone can. You must have some very special features, just like here. Must be the number integer, right? So you see the integer here. It can be 100 number. Can, all right? If you have 100 number, can. 1,000 numbers, also can. Your array bigger, but must be finite, must be finite. But real numbers cannot, because real number between 1 and 2, you have how many numbers between 1 and 2? Infinite number of real numbers there, right? So we cannot say how many of them. So that's why cannot. But for this one can. Must have some very special feature. Yeah, then you can do it. So near the end, so we have to go faster. So any questions? I cannot talk more, yeah, because okay, so this one also very simple, also special because of special case, it can be done very efficient. This one is how many times you need to do it, log n. Yeah, this one. Okay, look at it. So you have 5 numbers. 5 numbers is just an example, right? It can be 500 numbers, right? So how do you do it efficiently to sort it? 5, of course, you know who is the first one, who is the second one. 500 may not be that easy, right? But still, this one is quite okay. Because all of them are 4 digits, right? 4 digits. 4 times you can finish it. It's proportional to n. This one is proportional to n. Because how many elements you have. Okay, so this is also very fast under special case, right? 4 digits. Okay, so it's proportional to n, actually. It's proportional to n. 5, right? First of all, you do the sorting according to the last digit. So who will go first? 0 will go first, right? 0. This is 0. Then 4, and then 7, and then 8. These 2 guys are 0. Who will go first? Because this one comes first in this group here, this one will go first. This one will be the second one. You say, okay? This is called stable. It has certain meet certain requirement. Yeah, it's stable. This one is called stable. The standard term is. So our sorting is stable. If you appear first, you will go first. This one appear later than that, although it's both of them are 0, you will be number 2, right? Okay, stable. Okay, so by the 4th digit, 0, 0, 4, 7, 8. As what I have told you, 5890 will go first before this one because it's stable, because it comes first before that. Okay, now we base on this one, we sort the third digit. When we first sort the third digit, who will go first? 0 will go first. And then 5, right? And then 6, 6, 9. These two 6 are the same. So this one comes first, this one comes last. So this one should appear before that. So this is the answer. So as what I say, right? So this one comes first, this comes later. So because we want the sequence to be stable, so this one will appear first. Both of them are 6. Both of them are 6, right? According to the third digit. Okay or not? We sort the third digit according to this line here. Yes or not? You here compare 0 only, 4 only, 7 only, 0 and 8. Then 0 will come first. 0, 0, and then 4, and then 7, and then 8. I also highlight that, right? We don't care about the other. Okay, so make sure that you know what I mean. You try it first. Okay, so based on that, the second line, we sort by the second digit. 2, 8, 2, 6, 8. Number 2 should be earlier, right? But this one is stable, right? So this one comes first before this one. Okay, so it's like that. Okay or not? Done, huh? Next, we count the first digit. Once you finish it, suddenly the sequence is sorted, right? Correct. So I can't believe it when I was student. How come just do nonsense, right? Almost do it like that, huh? Then this one okay, huh? It's done, so computer can do it very fast, right? So this one is faster than you say that you compare this one and then you swap them. This one compare with this one, the bigger one swap it. It's like that, right? But this one, okay, you just do it. 4 lines, then you get the answer, and it's correct and it's stable. Stable in the sense that if this one appear in this sequence here earlier, will come earlier. Sometimes we need that. We need this feature. Stable. Okay. We need stable. The stability. Okay, not. Wow. So seems that you don't know, So that means the IRA you cannot finish it, So simple, right? Yes. Okay, next. Okay, how about the online student? Wake up. You see that, after 4 lines, we find the answer, right? Just cannot be easier, The sorting is from the last digit to the first digit, Cannot be from the first digit to the last digit. So this one is proportional to n. How many elements you have? How many elements you have? You just compare 1 digit. So cannot be easier, right? This one is interesting. This one, have you tried it? Probably not. When I deal with this one, I use about 2 weeks. I cannot find the answer. But later on, I find that I got a stupid mistake here, so cannot do it. So I tell you that my stupid mistakes are. So like that. So you have not many numbers here. Only 3 types of numbers: 0, 1, and 2. So this one is also very efficient because very special case. Now we are talking about very special cases, right? So this one is very efficient. If you have only 2 digits, 0 and 1, how to do it? One time in the quiz, I asked you, if you have 2 numbers, maybe 10 and 20, say like that. So how do you sort it? Wow, then they say that, oh yeah, how come you ask the sorting? Yeah, it's in the quiz. Yeah, you are not supposed to do the sorting. Yeah, right? You are not supposed to know the sorting. I say that you do the counting. How many 10 there? How many 20 there? Right? Then you get the answer, yeah. They use a very special case, right? Bubble sort, merge sort, right? Wow. All of them is not proportional to n. I say that is most efficient. Yeah. Okay. So don't worry about that. We look at it. Enjoy this one. Very intelligent. So 0, 1, and 2. You have only 3 types of digits here. So we would like to arrange them here in this way. So the first group will be 0. The second group will be 1. The last group, 2 right? The sorting is like that. Only 3 types. Yeah, only 3 types. So at the very beginning, so you know that P is the counter. P is the counter for 0. How many 0 are there? Q is the counter for 1. For 1. And the others, no need to worry about that. Once you finish up to n, it's done. Then you do the sorting like that. The counter is k, so you start from 1 up to n. K is just a for loop to look at it. So okay, an n element array A here. This one is an array, but the number will not be sorted. Contains only the numbers 0, 1, and 2. So you have to write an algo proportional to n to sort the numbers. Right? You can only do the swapping. Swapping 2 elements in the array. So you can only exchange their position here. How do you do it? Proportional to n. So also special case, right? It's not n log n. N log n, you have 100 methods to do it, right? This one must be very special. Okay, look at it. This one is the algo. We call it sort the array. First of all, we know how many elements there. If you, at the very beginning, P and Q are set to be 0. You don't have P, you don't have Q, right? Set to be 0. Okay. Then you use the counter K to look at the elements in A from the first element to the last element here. Okay, so the counting is very simple. If the element you are examining is equal to 0, then you update the counter P. P is equal to P plus 1 and swap the position of AK and AP. You swap them. Okay. And Q is supposed to be bigger than P, right? If Q is smaller than P, you set them equal. Set them equal. because Q cannot be smaller than P, right? You look at it, Q is on the right hand side of P, so it cannot be smaller than that. Once this one is dealing with 0. So how about if the element is 1, Q is equal to Q plus 1. So you update the counter for Q, and then you swap the position of AK and AQ, change them. Yeah, it looks very simple. So 2 years ago, when I deal with this problem, I used 2 weeks. I cannot verify that this is correct, because I have so many example try to use this algo. This algo is from a book, right? From a book. Unfortunately, it's an exercise, I think. So they just say that, like this, Then I try it, it doesn't work. It doesn't work. But later on, I find my answer, my mistake. This one is intelligent. Genius. Okay. And these are, to me, I admire it. Not very, very efficient. Okay. So you see that P is a counter for 0, Q is a counter for 1, Q cannot be smaller than P. It seems very simple, right? So how come it doesn't work, right? So we look at an example. This is correct one. So assume that we have 6 elements: 0, 1, 2, 0, 2, 1. We have 3 types of elements, right? 0, 1, and 2. At the very beginning, the P is 0. The counter P is 0. The counter Q is 0. The counter K is also 0. At the very beginning, we don't do anything. So no change. The element is like that. Now we examine K is equal to 1. When K is equal to 1, we look at 0. Once you see that it's 0, what should you do? Update the counter P. P will update. Once you update the P, Q cannot be smaller than that. You also need to update Q. Update Q. Update Q. So Q is equal to P1. So, and then you swap the A1 and A1. So special case, no change. Still like that. Now you go to the second element, 2. 2 is 1, right? 2 is 1. So what should you do? You update the Q. Q will be Q plus 1 is equal to 2. And then you swap the A2 and A2. So you also special case. A2 and A2 is the same element, right? No need to do anything. Okay, so now we examine the number 3 element, 2. 2 is 2, right? The number 3 element is 2. Once is 2, we don't need to update any counter. So no change. We don't do anything. This is 0. So this is 0. If it's 0, we have to update the counter P to 2. But Q is already 2, so no need to change it because Q at least as big as P, right? Then you swap the A4 and A2. A4 and A2. Yes, A4 and A2. So 4 and 2 exchange. This 0 is moved to here. This 0 is moved to here. So after that, the array becomes like that. Right? Now we have examined 4 elements. Now you look at it, the array. So this one is the problem, you see, because this one, if once we finish it, we come to here. We look at A4. Is it equal to 1? Now is yes. You look at it. This one here. You exchange, right? Here, let me see. A4 is equal to 1, right? Because once we do it, we swap it. So the 1 and 0, you exchange them. So 1 will move to here, 0 will move to here. Now you can come here. So now you examine the 1 again. Is it A1, A4 equal to 1? The answer is yes. So this one will execute. This is my problem. Because we think that we have update 0. How come we don't need to update 1? But actually you put 1 there. So now 1 will take effect. So we will update the queue. Once we update the queue, so A4 and A3 exchange. A4 and A3 exchange. So 2 will move to here, 1 move to here. So this is the step I always ignore. So it's not correct. So once we finish number 4, we go to number 5. Number 5 is 2, no need to do anything. Number 6 is equal to 1. We update the counter Q. Q is equal to Q plus 1, so it's equal to 4. So A6 and A4 exchange. So this one will come to here. This 2 will come to the end. So you see that the final answer is sorted. 0, 0, 1, 1, 2, 2. The problem is this guy. Because at the very beginning, we exchange the 1 and 0 here. So it becomes 0 and 1. Once you come to here, it becomes 1. So we need to update the counter Q. Once we update the counter Q, then we will exchange these two. So this is the extra step. I always miss that. Yeah, so that's why I don't get the answer. But you see that my answer should be correct, right? You can try yourself using other sequence, no? And it should work. Okay, no time. So any questions? Online students? Okay. Oh, bucket sort. Oh, that 1 minute. So if you have a sequence here, or below 1, it's just an example. Below 10 also can. Below 2 also can, right? So assume that is between 0 and 1 here. Don't say that is between 0 and 1. It's just an example. If you have something from 0 to 5 also can. You have more buckets here. Now from 0 to 1, we will divide them into 10 buckets. Or here, 11 buckets here. So less than 0.1 is here. Less than 0.2 is here. Less than 0.3, the rest, all put it there. So these 10 numbers, I think 10, 10 numbers here, we will place it in 10 small buckets, right? And each one is a linked list. Each one is a linked list. So because you have 10 only, now you divide into 10 buckets. So you will expect that in each one of them, you don't have many elements. The linked list is not very long. Probably 1, 2, 3, probably like that. It's very easy to do the sorting. So when you do the sorting, it's very easy, right? So after that, we do the sorting for each bucket. Okay, so you do it. This one, 0.4 should come first before 0.8. This one is 0.27. Comes before 0.28 and so on. All of them are sorted. And after that, how do we sort it? We just read it like that. This is the number 1, number 2, number 3, number 4, number 5, number 6, number 7, and so on until this one. Then everything is sorted. So basically, we divide them into small groups. And each group, the number of elements is small. So you can do the sorting very fast. You sort 100 elements and you sort 5 elements, they are very different, right? So that is the advantage of that. So this is called bucket sort. So you have an array of elements, yeah, between certain levels. You chop it into many parts, 10 parts, 100 parts. Each one, the number of elements is expected to be small, so you can do the sorting very fast. Once it's small, it's fast, right? And after that, you can just read it out like this, sequentially. Then you get the answer. Okay, so today you feel that a lot of special cases, yeah, for the sorting. Many questions to ask you. Okay, so try to understand if it's good enough. Okay or not? How about online students? Go to enjoy them. Important. Yeah, all of them are important. Now near the end. Okay, so today we stop here. Thank you very much.